Welcome back. Bill Gillespie here again to cover a little more material about Bayesian modeling, and today is our lab session. If you recall, during the last lecture I had assigned to you the hands-on example number 2 here, where we're going to be looking at population PK/PD modeling of some time-matched biomarker and PK/PD data. It's actually the same data we worked with in example 1, but in this case, instead of using time-averaged values where you only end up with one observation per individual, we're going to be working with the full time courses for all of the individuals, so that we end up with multiple observations per individual, and thus we're going to be handling this as a population model where we incorporate inter-individual variation as a component of our model. Okay, so we're going to be analyzing that data. Just remind you what it is. We've got our data from a parallel dose escalation design. We've got 8 subjects per dose group. We've got 10 dose groups. Then we've got PK and biomarker data at several times. You can see listed here out to 24 hours. And so we're going to take those 2 observations, match them up by time because they've been measured at the same times, and we're going to model those concentration effect curves, then using a direct action PK/PD model with some component of inter-individual variation. Just quickly jump through the data. This is, so in a sense, this is the way you're going to be viewing the data here. We've got factor 10A inhibition plotted versus the plasma drug concentration, and here the spaghetti plots here correspond to each one of the individuals and each one of these panels to the different dose groups in here. So these are the data we're going to be modeling, such that when we're done with our model, we will have actually in effect modeled each individual time course, or the time, or not the time courses so much as the concentration effect relationships for each one of these individuals. They'll share a common structural model, but with some inter-patient variability. The model I had proposed is right here. Our core structural model, you can see here, is a sigmoid Emax model. In here we have some residual variation in the form of just a normal distribution for that, and then we've got a single inter-individual random effect in here on EC50. So we're going to describe EC50 as log normally distributed, and the way I've written it here is by taking the log transform and describing that as normally distributed, and that's the way we'll work with it. Then I've got a few weakly informative prior distributions for our parameters in here. So that was your mission, and in particular your mission is going to be to focus mainly on the BUGS model itself. I'll go ahead and also do part of the R script while we're at it here. So let's see, orient you here where the stuff is. The stuff's all in this ME2 hands-on 2 folder. The data set we'll take a look at in just a second. Now there's actually worked out models and R scripts already there. My proposal to you is actually, or was to actually either delete them or hide them somewhere and use the dose response 1 example as a source of templates for building these up yourself. And what we'll actually look at today is doing exactly that for the BUGS model, and we'll also do at least the beginnings of the R script here. For the following week, what we're going to be doing is, well, for the lecture we're going to be talking largely about model checking and comparison, and some of the tools we're going to be talking about in there, particularly posterior predictive checking, is something we will apply to this example. So your assignment for the following week is actually going to be doing some posterior predictive checking on this very same example. But today we'll just kind of run the bare bones part of the example. Okay, let's see, nothing else there. Let's take a quick look at what the data looks like. The data you can see here, we've got, this is show you in its context here. So in the MI250 folder here. It is inside ME2 hands-on 2, and here it is, the fxa.data.csv. Now notice I've already deleted, or actually moved, the solutions here. I kind of just stuck them in a directory here down here, and I've already moved over the dose response 1 R script and bugs model here, and we'll edit those to build up our example in this case. But anyway, back to the data. So the data, we've got a subject identifier. I think I've already got it set up as a integer sequence beginning at 1, so I don't think we'll need to do any modification there. There's some covariates I'm not going to monkey with here, but if you want to, you can explore the notion of trying to put covariates on one or more of the parameters. So we've got weight, age, and gender there. Time, which in our case we're actually going to be directly modeling the relationship between the concentration and the effect, and we won't incorporate time directly. So time really only plays a role here as determining what concentration gets matched with what pharmacodynamic effect. Similar for dose, we won't be using that directly as a covariate in our model. We'll have our plasma concentrations labeled here as COBS, and our percent inhibition of factor 10A activity labeled as fxa.inh.obs. So the data set we're actually going to focus on is really just going to be the subject, the COBS, and the factor 10A activity here. So that's really all we're going to be working with for our example. So let's get to it. Let's get to Windows World here. Okay, so here we've got it here. Let's start building our bugs model itself. One of the things I'll start with, actually, let's rename these things to be consistent with the naming of our model directory here. Okay, cut that out. There we go. So we called it ME2 hands-on 2 .txt here. And we'll do the same thing for the R script. Okay. Yeah, let's go ahead and open up bugs, and we'll go ahead and edit our model right in there. Let's see here. There we go. Let me widen that out here. Get rid of the wrapping. Okay, and let's actually open up our the handout here so we can have the model. We can be looking at the model that I had in that. It opens in the right thing, yeah. Okay, hands-on 2, there we are. Okay. Let's get rid of this and make that a little bigger. I don't want fit page, I want fit width. Okay. Oops. There we go. Let's actually shrink that down a little here so we can, not too much. Okay. Okay, so we can see our model here. So it's actually gonna bear a lot of similarities to what we did in the dose response 1 example in here. But there are certainly a few differences as part of this. So let's see what we've got here. So Let's see, Emacs, we're not going to have any random effects on Emacs for one thing. So one of the first things I'm going to go ahead and do is take care of the random effects in this. Recall before we had the random effects on Emacs and the intercept E0. And while we're not doing that, we're going to be doing it on EC50. So let's just change some names here. We're going to go with log normal, so we'll do it the same way we did before with Emacs. We'll just really need to change the name here. Let's just call it EC50 there, and we'll do the same over here. Do that. I'm actually going to change the name on this here. In hindsight, I'd rather call it log EC50 mean or something like that. Mean or hat or whatever. Actually, I'll pick my favorite. Let's call it hat. Okay, and then we'll have a precision associated with it. I'll go ahead and use the same convention. I'll just call it tau EC50 in there. And we don't need random effect on anything else. So let's go ahead and rename this appropriately. We're going to call it EC50. And that's going to be from log E. So we're just taking the exponential so we get it into its native name there, EC50 instead of log. Let's do that over again in order for our to get our posterior predictions. Recall, if when we want to do the population predictions, we're going to need to simulate these individual random effects. So let me go ahead and create that here, and I'll just stick a dot pred on everything on these. Put a dot pred here. Let's see, we don't need to do that. The things on the right hand side here stay the same on those, because this is our inter-individual precision and our inter-individual whatever you want to call it, typical value there. So we only need to do that on the left hand side, and here we're going to take our log EC50 pred and convert it to EC50 pred. So that takes care of our random effects. There, we're all set there. Now we have to deal with our observations, where we're now going to be describing our likelihood in here. We're not going to recall before we actually had a log normal residual variation, which we're not going to have. So there is some nonsense we'll get rid of that we're not going to use. What I'll do is I'm going to start right from the top here and just take care of our normal likelihood right here. And I'm going to use the name FXA for the response when we create the data set, instead of that rather lengthy name that was in the data set. So we're going to get rid of this transformation nonsense here, and we're just going to call this FXA. Say right here, that's going to be normal. I think I'll call it again, you can sort of name these things anything. The trick here is when you write the R script, things have to be consistent in the two settings. So if I use FXA here, then that means in the data set that we send to bugs, it has to be called FXA. So I'll call this FXA hat, and then we have our residual variance. Now, in the example I did for dose response, that was a meta-analysis example where we were working with sample means, so we had to adjust the residual variance for the sample size. Well, we don't have to do that now because we're dealing with individual observations, so there's no sample size issue that we need to deal with, so we can get rid of that. It means we can also get rid of it right here. Okay, and so let's go up here. Now we've got to generate this FXA hat. That's what we've got right here. So that's going to be our sigmoid Emacs model here. So we need to do that. Notice before we used a plain Emacs model, so that's going to change. So let's go ahead. Let's see, we also don't need this conversion, this log conversion there. So it'll simplify. Let's just call this fxa hat then, fxa dot hat. We don't have an intercept anymore, so we can get rid of that. Because you see, as we did it over here, it's a sigmoid Emacs model with no intercept. So now we need to, let me check something real quick. Yeah, we're doing fine, okay. Okay, so let's see, fxa hat, so we're going to want an Emacs here for sure, and that's there, but now notice I had a random effect and a subscript here to deal with that. Well, we're not going to do that now. Emacs is now really sort of a constant in our model here. It's the same for all individuals, so no subscript there. Also, we're not going to be dealing with dose now. We're dealing with concentration, and I guess I'm going to use the name COBS here for observed concentration. Okay, so that takes care of the numerator, sort of, except we have one other stinker. Before it was a straight Emacs model. Now it's sigmoid, so we need to deal with this gamma, our exponent there. Well, the first thing I'd love to do here is I'd like to just maybe go something like that. And if I was dealing in Fortran or C or R or various things, that would work. However, there's no exponentiation operator in BUGS. There is, however, an exponentiation function. And so, let's go ahead and actually bring up the help file to remind you where you can look that sort of thing up. We go down, go into model specification, and to where it says, where are we, logical nodes. It shows you the list of functions, and if you look down that list, you'll see one right here called POW, or POW, which is, I guess, stands for power, and that's our exponentiation function in here. So it's a function with two arguments here. I always forget which ones I have, abscissa and mantissa, but anyway, so here it's showing us POW e to the 1, comma e to the 2, which would be give you e to the 1 raised to the power e2. So, okay, so let's go ahead and do that. All right, here, so we can't do this, so instead we're going to say POW, open parentheses, put a comma here and get rid of the two asterisks and a close parentheses, and that will give us COBS to the gamma. Okay, and then we go to our denominator. Well, we got EC50 now, not ED50, and now EC50 is specific to each individual. I just realized here, I think I used the name, I left it 1 to n study. Let's change that up here. Let's make it, oh, I don't know what would be good here. I guess these were volunteers. We'll call them subjects. So why don't I say 1 to n sub here for the, so we're actually going, that loop up there should be going from 1 to n subjects rather than n studies here. So I'll just call it n sub. And then in the data set, recall we have an identifier for each subject. We're going to make use of that identifier from the data set right here. So where before we said study I, we're going to say subject I. So again, we've got the nested indexing here, and this quantity subject has to be provided in the data set, and it should be a sequence of integers that goes from 1 to, well, 1 to n sub, and it's what, whoop, that was very clever of me, and that's what will allow us to appropriately match up the random effects that we get within the first loop with those in the second. Okay, so we do that, but then in addition, this needs to be raised to the gamma power here, so we put that in our pow function. We say gamma again here. Okay, and then we need to do exactly the same thing we just did over here with the concentration and raise that to the gamma power. So we'll replace dose with that. Okay, why don't I go ahead and maybe put in a carriage return here just so it doesn't run off the edge. Okay, so that's our, in fact I'll put it right there. Okay, so that's our sort of our structural model here, where we have used that nested indexing right here to pick off the appropriate individual specific value of EC50. So this combination then is basically is our likelihood function that we want here. Now we're going to want to do a couple of posterior predictions here. Recall we want to do individual predictions and as well as population predictions. And the individual predictions, you saw what we did last time for the dose response model. We don't have to deal with the log transformation, of course. So basically all we need to do is just take this function, this term right here, and I'm just going to repeat it. Now, actually, why don't I go ahead and change my, just so that our comments are correct up there. I'm going to repeat this then, except now I'm going to give it a different name, and I guess I'll be consistent with what I used the last time here. Call it fxa.cond, meaning that it is a prediction or simulation that is conditioned on the individual specific value of EC50, the one we've generated, that we generated up here. So, well, actually it was generated up in the previous loop, but the same one as that. So the right-hand side is the same, but again, the difference is in this case, fxa is data. It's a set of fixed values in our data set. In this case, they're not. These are going to be simulated using this normal distribution and the same value of fxa hat and tau that is used in the likelihood function here. Okay, why don't I go ahead and put this little comment up there here too, just for completeness. Except I'll say new observer. So this is a new observations in the same, in this case, subjects. Okay. So we took care of that. Now we need to take care of the population predictions, or predictions of new observations in possible future patients. So why don't I go ahead, I'll actually want to, oops, pushing the wrong buttons again. Go ahead and do that. And we're going to do more or less the same thing we did before, but what changes is now instead of just copying that last term, I'm going to grab both of these. Here, so both sort of where we describe our expected value as well as the final likelihood term in here. And we're going to make an fxa pred thing here. So we'll stick .pred all over the place here, and we'll put .pred here for our expected value. And we don't need to for most of these things. The key exception here is for our random effect for individual. We're now, instead of using the individual specific value, we're going to use a simulated value. Now the way we've done it is we've simulated the same number of values as we had subjects originally, and thus it still makes sense to use the describer here, because in a sense what we're doing is we're simulating here is new subjects that are otherwise identical to the existing ones, and in particular they're identical with respect to the independent variables, which in this case is the plasma concentration. So we're only doing a population simulation for the concentration effect relationship, not for the concentrations themselves, since we didn't model the didn't do a PK model as part of this. So we got the dot pred there. In addition, we carry that through then. So we've got our dot pred here and a dot pred stuck on our FXA. So that's now going to be simulated values for hypothetical new patients that are identical to our existing patients. And here, go ahead and delete the old stuff here. Okay, I think we're in good shape there. Let's come down here, and we got to clean up with our prior distributions are going to be somewhat different, as well as the fact I think I used some different naming conventions here too, so might almost be easier just to rewrite them from scratch here. So let's go ahead here. And okay, so what did I say? I said Emax is going to be uniform 0, 100. So we can go ahead and do that. That's going to be Emax. And again, remember this is a squiggle here because it's a we're talking about random variable generations, and that's going to be DUNIF for uniform. And it's going to go from 0 to 100. Oops. And then what do we have for our EC50, our log EC50 hat here? That's going to be normal 0 with a variance of 10 to the 6. So log dot EC50 dot hat. Let me scroll up, make sure that I think that's the naming convention I used. Yes. So that is going to be normal, which is dnorm, centered at 0 with a variance of 10 to the 6. So that would be a precision of 10 to the minus 6. So that would be 1.0 E minus 6. Okay. We're going to want. Now, we actually don't use the EC50 hat directly. It's kind of up to you whether you do this next step or not. But sometimes I like to have, just return the the population prediction in terms of the EC50 or whatever the sort of typical value is itself. So let's go ahead and do that. So I'll just say EC50 dot hat is going to be, now this is algebra, so it's a left-hand arrow, and this is going to be exponential of log dot EC50 dot hat. Okay, and what else have we got here? Then we've got our gamma, which is going to go from 0 to 10, uniform. So that's gamma squiggle dunif 0, 10. Let's see, and I think, what did I do for our variances? Okay, let's see. For my variance on EC50, trying to remember why I made them different, but I did. I went to 10 to the 5th there, and up to 1,000 for the sigma. So we're actually going to parameterize this in terms of the standard deviations for both the inter-individual random effect as well as our residual. So our omega dot EC50 is going to be dunif going from 0, and I said 10 to the 5th. Okay, and then our sigma, I said, oops, almost did the wrong operator there. Okay, sigma is going to also be uniform, but now 0 to 1. Oops, 1,000. Okay, but recall when we go up to our model that I didn't use standard deviations, I use precisions. So I've got tau.EC50 and tau here that are representing the precisions. So we need to go ahead and convert those to that. So to get tau.EC50, okay, so we've got to convert it to a variance and take the reciprocal. So we're going to say 1 over, and then to get the variance we have to square them. I'll just do it by multiplying here. Oops, what did I do? I missed a piece. Okay, how many syntax errors did I make today? Let's see. Okay, and we do the same thing for our residual term here. So 1 over sigma times sigma. There we go. So I think we've got everything there, and we can get rid of the stuff from the dose response 1 example. Okay, let's see. I think we've got all the pieces for the core model in here. Again, the key things in here is we've got, up on top here, we'll go ahead and separate them to see them clearly. We have a, actually let's indent that. We have a loop over all of our subjects, and that's where we generate our inter-individual random effects. And then we loop over all the let me change this too. Instead of calling it n-arm, let's use something more relevant here, which would be number of observations, which I'll just call n-obs here. So, and then we loop over all of our observations, and where we're just going to run through, basically stack all the individuals' data one after the other, and the way we distinguish one subject from the other in here is via a data object. The subject value here, which will be a vector the same length as our data set, is both our concentration and effect data, but which indicates which subject that particular data point corresponds to, and we use that to pick off the appropriate EC50. And for, I guess, all the remaining examples here, that's the basic strategy we'll be using to deal with a hierarchical or population model like this. Okay, let's see if we got it right. First of all, let's go ahead and save it. And then let's go ahead and see if we got at least the syntax right. Okay, check model. It says model is syntactically correct. Amazing. Usually I make at least one mistake somewhere in there. Got lucky this time. So that's the process of building a model, and sort of in this case building it using a template. So now we need to go to our R script. Let's see, I don't think we need this anymore since we've got our model structure already shown here in the bugs. Let's leave that together. Let me move it off to the side here. Yeah, let's fire up R. Okay, and let's open up MI250, hands-on 2, there we go. Let me open up that. Now, of course, this is for the dose response model 1. We're going to want to change that, so let's go ahead and just, for now, let me just say that this is, ME2 hands on, example 2, just to give our label here, and let's change our name to of our model to ME2 hands on 2. Be careful of upper and lower case here, because though Windows often doesn't care, R does. Okay, let's see. I don't think we have to change anything in the first bit right away. We come down, and the key things we're going to change are we're going to be dealing with the data set, and our initial estimates are going to be different. So let's go ahead and so what was the name of our file here? Let's see. Okay, fxa.data.csv. So let's change that to. I see this wasn't the modified one that we did, is it? Okay, well, it's close enough though. .data.csv. I think about the only thing I modified before, wasn't it? Was this thing here, CSV. I'll use read CSV. Actually simplifies it slightly. And just to be on the safe side again, we'll do an as is equals true here, just to keep it from creating factors when we don't want them. Okay, so now our bugs data set, let's take a look at our bug script here. What do we need? So in the data set we need our FXA, we need our COBS here, our concentrations and our responses then, and we need our subject identifier in here. So we'll need to pick off those. Let's did I leave that open? Yes, I did. So in the names that were used here, subject and COBS are the same, but I use the name fxa.inh.obs, so we'll have to keep that in mind when we create the data set here. Okay, so we need that. Oh, and we need the constants here, n sub and n obs as part of it. Okay, so we read that in. So for here we've got our n obs here, and this is exactly the way we'll do it again. It's just n row x data. Instead of n study here, this is going to be n sub, the way I set it up, and instead of study here, it's going to be subject. Okay, and here we need subject is our data item, and we change it on the right hand side too. Dose is not being used. Instead, well, the thing that plays the equivalent role here is our observed concentration, COBS. And we don't worry, n is no longer relevant here. And here, instead of RESP, we're going to have FXA. And on the right-hand side, recall it was FXA.inh.obs to match it up correctly. Okay, for initial estimates, well, let's get rid of method 1 here. Let's go straight to the one where we use the function. Okay. Where are we going to go? And I'm not going to even monkey with the fitting here. Let's just let's get rid of the fitting bit here, though we could actually do something like this if we wanted to. We're just going to eyeball it here. So we're going to need, let's actually write out the objects we're going to need, and then we'll figure out what they're going to be. We've got an Emax that we need. So we're going to need that. And then we're going to need we're going to need it's going to be what, log EC50 hat. Keep in mind the things that we want to specify initial estimates for. The main ones that we want are the things that appear down here in the prior distributions, and in particular the things that show up on the left-hand side of well, what they call stochastic nodes in bugs or distributions. So that would be, in this case, anything where you see a squiggle, you want that left-hand item. So we want Emax, log EC50 hat, gamma, omega EC50, and sigma. So we want initial estimates for all of those. So we can go ahead and say we want log.ec50.hat. Okay. Oops. And then we wanted gamma. And we're going to want our omega EC50 MI250 and sigma. I think we got them all there. Okay, so we're going to want all of those. Well, the way we're going to do some of these, let's see, for Emacs, well, one of the things, it's got to be between 0 and 100. And remember, we used this trick before where I actually used, what was it? I used a log normal distribution, but I truncated it on the upper end. So we'll go ahead and do the same thing here. So we start out with exp, then we're going to say rnorm. Actually, rnorm.trunc, recall. And we're going to generate one value every time this function's called. Well, where should we center this thing? Well, let's take a look at that, at some of those plots here. We can come up with some eyeballing here. Let me enlarge this a little. So if we just look at this fairly crudely, you can kind of see it whether we look over here at the individuals or even at this overall bunch here. Well, Emacs is getting up there. I mean, it's probably somewhere it's approaching, at least approaching 100 as we get around here. So, you know, I don't know. As I stare at this, I'm going to throw in, you know, I'm tempted to throw in an initial estimate that's somewhere around 90% on this thing. In fact, as long as we're eyeballing, let's also maybe try to eyeball our EC50 here. Well, if we think that somewhere around 90 is where the Emacs is, then we want to go to about half of that and come across and see where that falls on the x-axis. I don't know, is that any easier to see on any of those little guys? Probably not. You know, so you can kind of get a rough idea maybe. Actually, let's see. Might actually, because the scales are blown up a little here, we might be able to see it a little bit better slightly here. So we're talking about something a little less than 50 here. You know, so we're somewhere in the, I don't know, I'm guessing, you know, anywhere from around 100, you know, to 150 thereabouts is a rough guess. So let's go with 90 and about 100, I don't know, call it 125 here for these guys. So for Emacs here, let's say we're going to take the log then of, let's say about 90, and we'll throw in what amounts to a CV for the Emacs here. I don't know, throw in some value here. I don't know, 0.3 sounds as good as anything. I think we have a rough idea where that one's going to sit, and we need to put an upper bound on it, which is going to be the log of 100. Let's see, let's see, that closes out rnorm trunc, that closes out the exponential. Okay. For EC50 hat then, we'll do, there we don't need to take the exponential, we can go directly from our rnorm, say 1, and we'll center that at about, what did I say, about 125. And maybe make that one a bit more uncertain here, let's say around a 50% CV. And I think we got everything there. Gamma. That one's a tougher call, but as I stare at this thing, I'm not seeing any apparent sigmoid stuff here, so I'm guessing 1 and maybe even less than 1. So let's see here. So let's go ahead and center it at 1. We'll play the same game as we just did with the Emacs. In fact, if we want, we can actually kind of grab that. Come on, there we go. One too many commas there. Okay, so let's go ahead and center that at 1. We'll make that one a little bigger here. I don't know, 0.4, something like that. And our upper bound now is 10, as I recall. Yeah, that was our upper bound there. Omega EC50. Do we do the same? Yeah, we can do the same thing there. That one's a tougher call. I don't have a clear sense, frankly, on staring at this. There, inter-individual variability when I look at the spaghetti plots actually doesn't look that large. But I'll just go ahead and start out with a real seat of the pants number here, and go with something like I don't know, 0.25 here. And again, because it is seat of the pants, we'll put a fairly large CV there. What did we pick for the upper bound on that? 10 to the 5th, was it? Wrong way. Yes. Okay. 0.0E5. Okay. And we'll do the same thing for here. And okay, sigmoid or sigma. Let's see if we can come up with any magic. Whoops, wrong way here. There we go. Oh boy, I don't know. There is certainly a fair amount of noise here as I look in the on the y-axis here. Though at least some of that's probably inter-individual. And I got to remember now, in this case, we're actually talking. We don't have log normal, so okay. Yeah, let's just call it. Let's just center it at 10 and see where that gets us. Okay, again we'll put a. Now this one I have to remember. This is no longer would be. Will it? Yeah, it is still treated as a CV here, so it just goes 0.5 again. And an upper bound of 1,000, I believe I said. Okay, I think we got them all. Hopefully I got the syntax right, didn't make any typos. So that's our initial estimates. Let's get rid of the old ones. We have to say what we want to save here. Let's go ahead and fix that. Okay, we generally use different naming conventions here, so we'll certainly want our Emacs, our EC50. Actually, in particular, let's start out with our EC50 hat, our typical value. We're going to want gamma. And we want our variance terms, our standard deviations here. So we've got our omega.EC50. I forgot my quotes there. And what do we got? And then our sigma. I think that's probably all the ones I actually want to have detailed plots and statistics on, but there's certainly some others that I want to save. In particular, I'm going to want the individual specific values for the EC50. I want to save those, and I'm going to want my individual and population predictions. So that's our fxa.cond and the fxa.pred in here. Get rid of the old ones, and I think everything else is there. We're fine. I don't think I bothered to specify how many iterations or anything. Let's go ahead and start with the same as we did before here with the 3 chains, 10,000 iterations, 4,000 burn in, and we'll thin by 5. So I think we can go, well, let's go ahead and stick with that. Let's see. Oh, interesting. What did I do with my, I didn't have my debug on this one. Okay, well, we'll fix that. For now, for our first run here, let's do a clear WD equals false. And let me add in a debug option here. And oops. debug and make that true in case we encounter an error, which the first time we run one of these is usually the case. So we'll get that. I think everything else is okay there. And let's see where that's, the rest of this is kind of boilerplate. That should be pretty good. Pretty much right down to here. Where things change is for our posterior predictive distributions. We'll have to clean that up, though it will be pretty similar to what we did for the dose response one in this case. So here we'll change we'll change the comments to be consistent. Instead of talking about the same studies, we're actually talking about the same subjects, same individuals. So I'll do our individual predictions here, and we'll change the name to what we use, which was fxa.cond. And we need to change that here because our data was called FXA, so I changed that. That flew by real quick here. I just realized I kind of typed that kind of quick. That was in this line right here. And then we have to change the naming that we used inside the plot function here, xy plot. So we're now going to make this FXA. And instead of dose, it's our COBS. And instead of plotting a separate panel for each study, it's now each subject. Let's see, other than the labels, yeah, we'll change our X and our Y labels here. So for our X label, it's now going to be our MI2. I think I used capitals, didn't I? I forget. Plasma concentration. And for our response, it's going to be our factor 10A inhibition in percent. And I think that's all I need to change for that. And to save us the grief of the editing for the population predictions, we can actually, let's just grab this whole mess, assuming I formatted that correctly. Let's copy that, and let's repeat that here, except we're going to change the name of this thing to pred. And I just noticed I didn't actually label the plots themselves, so that when they're done, you know which one's which. If you want, you can do that something like this. If I say main, that's what we use to create the main a caption for it. So we can say main, and I'll use the same sort of formatting strategy we do for the labels here. So I'll just be lazy and copy that and edit it. So we've got, and we're going to need one more parentheses there, I believe. So here didn't I? Oh, I see what I missed here. I missed the, this is what I actually wanted on there, but I'll just type it in. Yeah, I wanted the label will be the thing that we're going to say, which in this case is going to be, individual predictions. And here I'll put in, or what did I want here? The CEX equals 1.2. Okay, and I think I've got enough parentheses in there. And we'll actually modify the one we were just making down here accordingly too. Let's stick that on at the end. I think I ended up with too many parentheses. There we go. Okay, except this one's going to be called population predictions. Okay, I don't think I finished this. Let's say I said the pred, that's taken care of. I think otherwise we're okay. I think we're okay. And let's get rid of the junk down here that was from the dose response 1 example. Now, if I did this correctly, it should fly. No doubt I probably made an error somewhere, and let's find out. So let's do, first of all, let me save it. Okay, let's just go ahead and let's be brave and run the whole thing here. Do I want to do that? Well, you know, the way I usually do these when I'm not sure, when I'm doing it for the first time and suspect I'm going to make an error somewhere, I usually actually copy, first of all, down to here to see if I made any errors in the data management part of it. So I'll run, so I've copied it down there and then run here, and I did. I can see I've got errors popping up already. Oh, it's because I didn't copy the whole, somehow I thought I copied the whole thing, but I didn't. I thought when I put that there, it would copy the whole kit and caboodle. Didn't it? It did that time, I believe. Okay, so far so good. Okay, let's see. Well, I don't have any syntax errors. There's no error messages there, so far so good. So let's see what happens when we actually run bugs itself. So I'll just grab this here, select that, and go ahead and run. Okay, it didn't upchuck at the beginning, so it meant the data structure and all that it's probably okay with. This is certainly a larger data set than the meta-analysis example we did before. As a result, it'll take a bit longer to run. I forget how long. I should have checked that before I started this today, but we'll keep an eye on it and see when it comes to life again here. And actually, when we finish this, that's where we're actually going to cache it in for today. And actually, while it's running here, I'll mention. So what we're going to be talking about, I think I already mentioned that next week we're going to focus on model checking. You know, basically on what I think I termed in the lecture model evaluation and comparison. So that'll take up, I believe, the entire lecture. And then what I'll do at the end of that, I'll be assigning further extensions of this example. And in particular, I'll be describing next week various approaches to posterior predictive checking, and I'll be assigning you the task of implementing some of those approaches for this example. Okay, where are we? It'll let us interact with it. No, it won't. And anyway, assuming this does run correctly, I'll try to remember to go ahead and post the result of this, the worked example I just did here. I'll post those on the website, so you have access to those. Dumpty dumpty dum. Yeah, and but one thing with bugs, unless you control it otherwise, you can interact with it only when it hits a refresh point. And by default, it only refreshes every, I was going to say 100 iterations, but it's actually every 100 times thin updater thing. So in this case, that means it's actually only going to come up for error basically every 500 iterations for the example we've got here. So there we go. Let's hit the update so we can actually see where we are. So what I'm doing here is I've used the model pull-down menu there and hit update. That way we'll actually see how many updates it's at and how fast or slow it's actually going. but it won't actually respond to my my mouse input until it finishes another 500 iterations. Okay, so we're up to 600. So we're about that puts us what is it here? About that's what did I say? That would be 3,000 out of the 10,000 total that we're going to be doing in terms of iterations per chain. Let's see if we can get to another thing you can do that that is sometimes that I often do, but and it's probably really not particularly useful, but I guess it's useful only in the sense of I guess giving you a warm fuzzy that something's actually happening, is you can run a trace while this is happening, and you can see the sampling going on. That's what I was about to try to do here. Let's see. Yeah. Okay, you can see it finished the burn-ins, and now it's about to start the, or it's in the process now of starting the samples where it's actually going to be saving values of our various different random variables here. By the way, you'll see that error. I keep forgetting about this one where it says the DIC set cannot be executed. And there's a couple of contexts where that can happen, but one is if you try to set it while it's still in adaptive mode in your sampling, you'll get that. And unfortunately, because I only gave 4,000 iterations for the burn-in, and 4,000 is the default adaptive phase for one of the samplers. If I had said 4001, it probably would have allowed me to do the DIC set. And all DIC set does is it initializes something that allows you to later calculate something called the deviance information criteria, which we'll actually mention. We'll mention next week when we talk about model checking and comparison. So we won't be able to get the DIC out of it because of this. If I had done, say, 4001 or 5000 as burn-in, it probably would have allowed us to get the DIC. Okay, why is this thing not letting me change this? So it moves. We're up to 1,200 iterations. So you may want to go ahead and fast forward the recording as you're watching this. And that's real exciting. So, okay, actually, I'm getting tired of looking at that myself while it's going. Why don't I move up here, as long as we're talking about what we're going to be doing next week here. This is just give you the lead in. If you wanted to read ahead, this is the place to start looking. So I'm anticipating what we'll probably cover in the lecture will take us through that. And let's see. Yeah, we'll cover that. So we'll probably go from, what is that, page 90, slide 96. Yeah, we'll cover the deviance information criteria, and yeah, I think that's where we'll get to. So what was that, 96 to 111? So I think that's probably the topics that we'll hit on. So if you wanted to read ahead, that's there. And I guess as long as I'm giving previews here, the week after that we're going to be focusing on such things as how to use, well, basically what will be leading into are tools needed to do population PK and PK/PD, where we want to deal with more complex models than the standard WinBUGS allows you to do. And I'll be introducing BUGSModelLibrary that lets you do a full set of PK models, in particular compartmental models that you can describe in terms of ordinary differential equations. So those will be that'll be the big focus of the week after that. Okay, let's see if it's, where are we at here? 1700. 300 more to go. And as long as we're talking about that, if you wanted to read ahead for that, I believe in the course docs folder on your drive, yes, I did. I provided you with the BUGSModelLibrary user manual here. Now a big chunk of it's devoted to how you install it. For the purposes of our course, you actually don't have to worry about the installation because I've already provided you with an installed set of the BUGSModelLibrary. So if you were going to be reading ahead as a starting point, I would focus more on the introduction section here, skip over the installation part of it, and then go to the simulated examples and start there, because it uses the simulated examples as the device to show you how to use different components of the model library. And almost there. Yay, we're coming to the end. Okay. Says it's doing the coda. Let's make sure it's actually finished dumping those files before I shut it down. Recall that I had set debug equals true, so it won't actually shut down until it's done. Let me do a refresh here and see what it says. Okay, coda. No, it hasn't finished writing the coda files yet. Oh, I see. It's got an hourglass there. So what it's doing now is it's writing out these so-called coda files, which contain the MCMC simulation results. In fact, you can see it just dumped here coda 1. So you can see the reason I knew is I saw they were only 1 kilobyte here, but now they're showing up at around 30. What are they? They're around 37 megabytes in each one, and it looks like it's done. It's okay. It's going through the history and so on. It's saving the log file, and I think we're there. Yep. I think we're cool. Okay, so it's finished running that. Let's go ahead and quit out of that. Okay, and it should return control to R, though it takes a minute because it's got a chunk of stuff that it's got to read in. Basically, what it's doing is it's now reading those coda files into R and putting it into an object that we call bugs.fit. So it takes a little bit to do that. So, and as you can imagine with whatever we got here, so we've got 37 times 3 megabytes for it to pull in, so it takes a few minutes to get its act together around that. And there we are. So we've got control back. So let's go ahead and finish this off then. So we're going to go ahead and have it, let's start by going ahead and having it save stuff here. So it should be creating a new folder, which it has, where it's saving stuff into it. Okay. Okay, you should be about done by now. Let's see, I guess it's probably dumping that bugs fit object again. Okay, it looks like it's taking care of that. And we're back. Okay, and let's finally go down and create our plots, etc. here. Oh, sorry, I scrolled way too fast. There we go. Let's go from there all the way to the end. Run all that stuff. So it should be creating us a bunch of plots. It is. Oh, I made an error someplace. Probably messed up on naming someplace here. Oh, I know what my problem was. Yes, I did make an error. It's in the right here. Recall that the original this original thing comes from Xdata, and I didn't call the factor 10a inhibition fxa in the data. It was called fxa.inh.obs. So that was my mistake there, and we have to clean that mistake up all the way through. So let's see, we made that error there, and fix it there, and I think it's pretty much the same all the way through. Whoops. Okay, let's go back and have it rebuild our plots here. Hopefully I got it right that time. Hasn't complained yet, so that looks a little more promising. Okay, and let's go up here and see what we got. Okay, so we have, let's look at it from here. There we go. So we can take a look at our, let's go ahead and take a look at the pictures. We've actually kind of gone over our scheduled time here, so just run through the pictures now. I'll let you look through the table of estimated values and such, but things are looking pretty good. Things are pretty much fuzzy caterpillars. There's a bit of autocorrelation apparent in a like an omega EC50 and some an EC50 hat, and maybe even a little bit in Emacs, but it's not bad. I suspect the effective ends are reasonable. And then you have your densities. We got our Gelman-Rubin-Brooks plots, and if we look through those, you'll see those are all consistent with the notion that we've at least converged. They're all have gone down well below 1.05. Here we've got, oh, I stuck them all on the same. I wish I'd broken these up by dose. In fact, well, I might show you that later. I believe when I did this before, I actually broke these up by dose groups because it's really hard to see the fits when I do it this way. But if you look hard, you can see that the fits in these things. In fact, if you like, you can take that as an exercise. How do you modify this so that you get a separate page for each one of the dose groups? And there's our population ones. Okay, as I say, we're already kind of past our time, so I'm going to close it out here and look forward to talking to you again next week. Bye for now.